Modeling complex systems, from the oscillation of a bridge to the behavior of electrical circuits, requires us to move beyond first-order calculations into higher-order differential equations. We begin with the initial value problem, or IVP. This defines a requirement where our solution curve must pass through a specific starting point at a single value of x. This source outlines the conditions for the function and its derivatives. Alternatively, some systems are defined by multiple physical constraints. This is a boundary value problem, or BVP. Here, the dependent variable y is specified at two different points, marked as A and B. A BVP is a set of conditions that specify how a solution must behave at the boundaries of its domain. To manage these equations, we often focus on the homogeneous state. This occurs when the right-hand member, f of x, is equal to 0. In this context, the equation describes a system's internal dynamics without any external forces acting upon it. Identifying these boundaries and confirming the homogeneous state sets the stage. These constraints allow us to apply the specific mathematical principles needed to construct a complete solution. Our primary tool for building these solutions is the superposition principle. This states that any linear combination of solutions to a homogeneous equation is also a valid solution. A linear combination is simply a sum where each function is multiplied by a constant. The principle is best seen through a standard second-order equation, y double prime plus y equals 0. By substituting the functions into the equation, we can prove that cosine x and sine x work as individual solutions. Because the equation is homogeneous and linear, the superposition principle allows us to combine them. As shown here, the function phi of x, which is constant 1 times cosine plus constant 2 times sine, retains its validity as a solution when tested. This provides a scalable way to build complex mathematical models. By weighting and merging simple building blocks, we can map out a comprehensive solution space that adheres to our original physical rules. Superposition is the engine of our analysis, but it relies on one critical assumption. Each building block must contribute unique information to the system. The superposition principle fails if the solutions we choose are mathematically redundant. If we attempt to combine functions that contain the same data, we lose the ability to describe the system's full range of motion. This redundancy is called linear dependence. As defined here, a set of functions is linearly dependent if at least one of them can be expressed as a combination of the others. Effectively, one function is hidden within the information provided by the rest. The simplest version of this occurs when one function is just a constant multiple of another. If your two solutions are just different scales of the same curve, they are dependent. They don't offer the unique mathematical dimensions required for a higher-order solution. Consider sine of 2x compared to sine x times cosine x. Because of trigonometric identities, these two curves carry identical information. They are redundant. They fail to meet the requirement for independence needed to solve a second-order system. To finalize a solution, we must prove our functions are linearly independent. This means no function in the set can be created by scaling or adding the others. Verifying independence becomes difficult as we move into systems with 3, 4, or n solutions. To solve this, we rely on a specific type of determinant calculation. We call this the Wronskian. To build it, we construct a matrix where the top row contains our original functions. Each row beneath that is populated by taking the next derivative of those functions. A matrix is a rectangular array of numbers or functions, and its determinant is a single scalar value that reveals specific properties of the set. The Wronskian provides a binary diagnostic result. It is the final validation required to confirm our solutions are independent and the model is sound. Testing functions e to the x and e to the negative x, we place them in row 1 and their derivatives below. Multiplying the diagonals calculates the determinant. The terms cancel, leaving a result of -2. Because this result is not 0, these two functions are proven to be linearly independent. They are mathematically distinct, meaning they can be combined using superposition to form a valid general solution for a second-order equation. By defining the environment, leveraging the superposition of parts, and using the Wronskian to verify those parts are unique, we complete the formal process for solving higher-order linear equations.